gonna be learning about how to create histograms using the image intensities and looking at the image intensities to see if the image has more background, which will have pixel values of 0 because they are black, or if it has more brighter areas or grayish areas. We'll look at all of these, and then we'll learn how to normalize our images using the cumulative distribution function, and then we'll also create some basic masks by setting a threshold. So without further ado, let's start. In my Medium article, I had found a fracture image, but I don't know where I took it in Kaggle because there are a lot of data sets. So I took this instead, and we'll have to work with this one. But it's pretty similar to the one. I'll change the name to phone.png. And after that, I'll import image.io that version 2 as image.io, and then I'll also import matplotlib.pyplot as plt, and I'll be reading the image using the image.io.imread function. And this time we don't have a fracture.jpg but a bone.png image, and I'll quickly print it to look at the shape, image.shape, and then of course the minimum pixel value. The fracture image that I found was a really good example because it had 0 to 255. Hope this is a good example too. That minimum, and then print single pixel value using image.max, and then I'll show it this time not with a subplot but with plt.imshow, and you'll do it with a gray CMap. I don't want the axis, and let's show it. Okay, so this is good too because it's grayscale. It's usually easier to work with grayscale images, but I'll show how to turn the images with a color channel to grayscale too, but it's in the following parts, maybe part 6 or 7. Let's see. But it's good that we found a good example. I hope we can clearly see the pixel intensities with the histogram too. Let's look at it. So here, when you are training, I didn't want to pass this without saying this. You have to resize it if your GPU isn't powerful, and GPUs usually, if you have a lot of images, they want something, for example, like 256 by 256, and my GPU sometimes even says out of memory for that. So I might do 125 to 28 to 128. It's important that they are divisible by 8. So if you wanted to build a AI model out of this, you would want to resize it. I just want to mention that before passing. So it's important to always look at the shape. And then the minimum and maximum functions, as you know, return the darkest and brightest pixel values in the image. And for grayscale images, these typically range from 0, which is black, to 255, which is white. As you can see, we have some whitish areas, but these are grayish. I think this is the part that makes the maximum 255, and the background is 0. And by analyzing this range, we can determine if the image has high contrast or if some regions are underexposed, which we will see more when we visualize these values with a histogram. So basically, a histogram is, just to make sure I know you know all of this, is a graphical representation of the number of pixels at each intensity value. For example, if many pixels are dark, which is usually the case, the histogram will have a peak at lower intensity values. And let me show it to you. So now we'll be introduced to SciPy library SciPy.nd image, which we'll use all throughout this series, and it's really useful for anything like transforming the image, applying filters with convol function, etc. So I really love this library. For creating an histogram, we'll just say ndi.histogram, give the image, give the minimum value we want to see in the histogram, the maximum value, and we'll show 256 bits. So we want to see how much pixels have that intensity value for each of these intensity values. and then we'll plot it and show it. So here you can see it, and as we can see, most values are in the lower intensity part from 0 to maybe 25, and we have some peaks here because most is it's like these are black, all black, these are gray, and it becomes brighter and brighter. That's why maybe these peaks, and we have some grayish values, and we have also a kind of a peak. We can't call it peak, but kind of an increase in the 250 because of this writing here saying left, I believe. And if you want to, let me copy this, show a specific part. Yeah, maybe let's look at to 25 because this is the part where something's happening. And 26, oops, bins. You can see these three peaks, and this is the pixels, how many pixels we have for 0 to 25 intensity values. And oops. So let's see. Now I think we are done with the histogram part. We understood how to analyze it and interpret it, especially. We can now look at normalization. So for normalization, I'll take my original histogram with the full range. Image minimum 0, maximum 255, pins 256. And then now let's call the cumulative distribution function. We'll take the cumulative sum, so it will sum up every value, like how many pixels there is for each intensity value by rolling over the histogram, if you want to imagine it, and then like all of the pixels, so that we'll get the in like kind of density, if you imagine it like a density plot of each intensity value, and then this will normalize it, because it's like you are taking the full and then that specific value, and if you divide it, you'll get a kind of normalized image. And then I'll of course show it as a subplot, but I'm kind of tired of writing n rows and n columns, so I'll just write it. And while I'm writing, you actually see what I write here. Now it's time to write n columns, and that's all. Okay, x is 0, that I am shown. I'll show the image, and then the CMap is not that, it's gray. And then wait, I didn't even equalize the image. Sorry. The equalized images, because we have 255 at the maximum, we'll say we'll put the image into cumulative distribution function and then multiply it by 255, and we are done. So, equalized image CMap gray for x in axis start axis of, then plt.show. Now let's see. And here you can see, now we can see the bones more clearly. If there was a fracture, we would have seen it more clearly. So the normalization is good for this case, but it's not necessarily good for biomedical image analysis, because it gives importance to the background, and we don't want to give importance to the background. We want to kind of emphasize the foreground, which is more emphasized here. So it depends on the situation you want to use it, but it's a good tool to keep in mind. But we have to be careful. After that, I'll also show you the CDF plot. I'll just let me copy paste this, and the remaining is easy. Just make two subplots again. Subplots 1, 2. No, not 1, 2 this time, because the plots are like this. So it should be 2, 1. I'll have 2 rows. This is 0, but show, not I am show this time, it's plot. Plot histogram, label histogram, axis 1 dot plot CDF, label, oops, label cdf plt.show. Let's see. And here you can see it shows the CDF plot, and we can see that 0.6 of the, like, all the pixels is in the like 0 to 10 range, maybe 20 range, and the others like the white areas are basically too little, and the black areas dominate the image, we can say that. And the histogram, we've already talked about that. Okay, now what do we have? We'll create masks, but it's not a Halloween mask. We'll do binary masks. So masks are basically logical arrays where pixels meeting a condition, which is like a threshold where we say intensity greater than 32 are set to true and others are false. This helps isolate regions of interest like a tumor, or a, I don't know, anything else maybe, or an organ maybe, such as or bone tissue in medical images, and this will especially be very easy with numpy.var, but we'll talk about in the third part. Also, by combining masks, we can isolate specific structures like non-bone tissues, which I'll show you. With a simple mask, we can take the bone tissue, like the whole tissue and the bones, but we will combine them to get to the non-bone tissue. So without further speaking, let me show it to you. Mask one is, let's take image, the pixels that are that have intensity values greater than 32, and I'll just show it. This is that simple. One cmap gray dot access of dot show. And here you can see the whole tissue basically. You can play with this, say make it 40, it will be thinner. Make it 50, it will be much more thinner like this. Let's keep it in 32 for now. Now let me show you how to take the bone. We'll take a higher value. It's not exactly, but it's kind of the bones. But if we take 80, yeah, like more bones. But I'll take 64. And then if we combine it with mask 3, we'll take the intersection of mask 1 and the areas where there is no mask 2. We don't want to take the bones so that we can take the non-bone tissue. And to do that, we use the tilde symbol, this one. And it says don't take mask 2 basically. Did I? Oh, I didn't even create a mask 2. Let me run this again. Okay. After that, we again plot mask 3, cmap gray, that access of, yeah, that's show. And here we can see the non-bone tissue basically, which is very, very cool. And this was all from this part 2. In the part 3, we'll talk about some more advanced maskings with numpy.var, and also we'll look at how to like apply some filters with NDI, like this ndImageLibrary.convolve function, which will be also very cool. And we'll apply these filters with some matrices. And in the fourth part, we'll move into more advanced filters that we know, like the Gaussian filter, median filter, etc. So it'll be even more interesting, and I'm looking forward to seeing you there in those videos, and I hope you learned something, and see you in part 3. Bye!